So have you, okay, today let us talk about some generalized functions. Okay, so the first thing we are talking about is the theta function, or it's also called a Heaviside function. Okay, so have you came across the function where theta of x is equal to plus 1 if x is greater than 0 and 0 otherwise. Okay, so this is called a Heaviside function. So if you plot this, what are you going to get is, so x, so you get 1 here, okay, so 1 here and 0 here, fine. So you already know the sign function, that is epsilon of x, right? You know this one, right? So can you find out the relation between theta of x and epsilon of x? Can somebody tell me the relation between theta of x and epsilon of x? Where epsilon of x is plus 1 if x is greater than 0 and minus 1 if x is less than 0. Can you hear me?
Yes, sir.
Yeah.
Yes.
Yeah. So what will be the relation between epsilon of x and theta of x?
Sir, epsilon of x equal to theta of x if x greater than 0. Otherwise,
No, I am saying because write a relation between epsilon of x and theta of x. So it is very clear. So what is the definition of epsilon of x? Plus 1 if x is greater than 0 and minus 1 if x is less than 0, right? Yeah?
it can be write it as epsilon of x equal to theta of x multiplied by p, where p we can define.
So what I want to do is, see, I want to write epsilon of x equal to in terms of theta of x. Okay?
Sir, is it so is theta of x equal to mod epsilon of x?
Okay, I'll give you 2 minutes. You just find out. Yes? Nobody got it? So theta of x minus theta of minus x. What is this? Is this correct?
Yes, sir.
When x greater than 0, theta of x is plus 1. This is x greater than 0, theta of minus, so it will become 0. When x less than 0, theta of x is 0. So this is plus 1 minus plus 1. So you get, so this is the relation between epsilon of x and theta of x. Okay? So So can you write down a relation between theta of x and epsilon of x? So can I write now? So this is how relate theta of x in terms of epsilon x. Now epsilon of x in terms of theta of x. So can you rewrite this? So that the right hand side should have a epsilon of x. Now you got the idea. Can you just give me the answer?
Sir, is it mod epsilon x?
No, how can be mod of epsilon x? Okay, let us see. So you are saying mod epsilon of x, whether it is correct or not. Okay. So if x is greater than 0, what is epsilon of x? Plus 1.
1, sir.
You get answer 1. When x is less than f0, what is epsilon of x? Minus 1. So modulus of minus 1 is 1. So you get theta of x is 1 always. So that is not correct. Okay. So from this you can actually get that. Okay. So let me write down 1 plus epsilon of x divided by 2. Is this correct? See whether this comes to be right.
Yes, sir. Correct, sir.
Correct. Okay. So this is another relation between the Signum function and the Heaviside function. Okay. So can you find out a relation between tan hyperbolic x and epsilon of x? Because you know, so how does this tan hyperbolic x looks like? See, if I am going out of board, you have to tell me, okay? So how does this tan hyperbolic x looks like? It goes to 1 and minus 1, right? This is minus 1 and this is plus 1. So you know that epsilon of x is plus 1 for greater than 0 and minus 1 for x less than 0. So how can I get a relation between epsilon of x and tan hyperbolic x? So basically what I am saying is, so can I write epsilon of x in terms of tan hyperbolic x?
Sir, could we write it as limit a tends to 0?
Okay, so suppose I have ax here, where a is a constant, a positive constant, say. Okay, so if a is equal to 1, the slope at here is at x is equal to 0 is, when a is equal to 1, what is the slope of tan hyperbolic x at x is equal to 1? X is equal to 0, 1. So when I increase a, okay, so suppose I put a is equal to 2. So what will be the slope at x is equal to 0? Any idea whether it is going to increase? Yeah? Yeah? We were saying something, Krishna?
No, sir, it's not me.
Okay, somebody else is speaking. Okay, so if a increases, whether slope increases or decreases? Yes? Decreases. Increases or decreases? Increases. Okay, so if I put divided by a, x divided by a, so if I take limit, okay, a tends to 0, what happens? The slope will keep on increasing and this function will become epsilon of x. Okay, so the relation between the epsilon of x and the tan hyperbolic x is, okay, so I can put a tends to 0. So tan hyperbolic x divided by a. So now let us look at the box function. So what is the box function? So say this function f of x. So this is, suppose this is say x0, and this is minus epsilon, and this is means x0 minus epsilon, and this is x0 plus epsilon. Suppose I want this area under this function is 1. So how do I get the area under this function 1? Because this is what is the length? What is the length here? Yeah? 1 by 2 epsilon. So if I keep this one as 1 by 2 epsilon, okay, so I can define the box function as f of x is equal to, what will you write? 1 by 2 epsilon when x between, okay, I'll write x between x0 minus epsilon and x0 plus epsilon, 0 okay. So this is my f of x now. Yeah? Okay, fine. So f of x is equal to 1 by 2 epsilon when x is between x0 minus epsilon and x0 plus epsilon, and 0 otherwise. Okay? Yeah.
So what happened at x naught minus epsilon when x equals to?
X naught?
When x equals to x naught minus epsilon, means at that point.
X is equal to x naught minus epsilon.
Yes, sir. Yes, sir.
Okay, so basically what generally do is basically this, see, up here it is 0 and here it is 1 by 2 epsilon. So for calculation and other purpose, people take the average of these two. So that means 0 plus 1 by 2 epsilon divided by 2. Okay. So even this is true for our theta of x function also. So theta of x function at x is equal to 0 will be half. That is the general notation. Okay. So yeah. So now take this box function. So this is basically called box function. So all of you pinned me, right? So I did not means spotlighted me. So all of you are able to only see my screen, right?
Yes, sir.
Okay, okay, fine. So the box function, suppose you take limit epsilon tends to 0, limit epsilon tends to 0, f of x, where f of x is the box function. What is that equal to? What will, yeah? So this will become delta of x. Okay. So you must have studied this already in your electrodynamics course. So,
delta of x minus x.
so that is the thing. Okay, so this is, okay, so limit epsilon tends to 0, f of x, where f of x is the box function defined in the earlier, and this is equal to delta of x0 minus x0, x minus x0. Okay, so you already know the properties of, so now let us get into the delta function.
Sir, I have a question, sir.
Yeah.
Sir, for the box function, how do we notate where the x0 point is? Because for the function definition, we just wrote f of x and then x between x minus epsilon naught, x0 minus epsilon and x0 plus epsilon. So how do we denote which point x0 we're talking about?
X naught can be any value in R. Okay, I can choose x naught anywhere. Okay, so it does not matter.
No, I'm asking, don't we need to write that in the function also?
Pardon me, can you just repeat?
So don't we need to somehow write that in the function notation also? Otherwise, how will we know which point we're talking about?
Okay, so if you want, so instead of simply saying f of x, okay, so you can put a box function around x naught. Okay, so you can do that. Okay, so that is fine. So okay, fine. So what are the properties of delta function? Yeah.
Did the theta and epsilon function had any names other than epsilon?
Yeah, the epsilon is called a sine function or a signum function. Okay, and theta is called a Heaviside function. Okay, so that's, so maybe avionics. Have you have any class on avionics? This communication class. So they may be calling something else also. Okay, so let us now say that it is an Heaviside function. Theta of x is an Heaviside function, and epsilon is a sine function or signum function. Okay, so delta function, which is basically delta x minus x0. So before, see, this is a continuous function, right? X is continuous. So before getting into that, let us, so Chronicle, okay, function which is denoted as delta ij. So what is I? So ij can take any values from 1 to any n, capital N. Okay, yeah.
So it's not visible. It is
Yeah, so let us look at delta ij. Okay, so delta ij, which is called Chronicle Delta, and this is defined as equal to 1 if x is equal to, if I is equal to j. You must have already heard about this in your previous class, and 0 if I is not equal to j. And so what is I and j? I and j can take values 1, 2, 3, etc. Okay. So this is discrete, basically, Chronicle Delta. So later on in the our class, you will see that this is basically a tensor of rank 2. So that we will discuss later. But right now, just understand this as a functional point of point. It is just a discrete function which is equal to 1 if I is equal to j and 0 if I is not equal to j. So delta function, you know that if function will goes to infinity when x is equal to x0, otherwise it is 0. And there are some properties of delta functions. So can you tell me, suppose delta x minus x0 minus infinity to infinity dx. What is this equal to? So this is 1 because see, you already saw that in the box function whether you decrease, so in this case, in the case of box function, when you decrease this epsilon, the height keep on increasing. So, but the height into the width will always become, because that is the area of this function. So, you can see that it will always 1. So, minus infinity to infinity, when epsilon tends to 0, this area under that curve will be equal to 1. So, this is equal to 1. What about x0 minus epsilon and x0 plus epsilon? What will be this equal to? This will be, this also will be 1. So, what about plus epsilon to plus 2 epsilon? This will be 0. Okay. So, if you have any questions, you should ask, because you have already learned this. So, I am not explaining more. If you have any problem, you stop me. Okay. So, there is no issue. So, because this x0, this delta function, the integration does not contain the x is equal to x0 value. So, because of that, this integral will be 0. So, what about minus infinity to infinity dx f of x delta x minus x0? This is f of x naught. Okay. So, this is very important. Okay. So, yeah. Yeah, so I think I should put this one here. So, this is equal to f of x naught. Okay, because this is based. Yeah.
So how it comes f of x naught? I'm not getting.
So again, let us go back to the box function. Okay. So now I have a, so this is box function. So that is f of fx naught. Okay, you did not like that. So there is another function g of x. Okay. So this is g of x. So box function is there around x0. Okay. And there is a function g of x. So if I multiply g of x and the box function and integrate from minus infinity to infinity, what I am going to get? So I am multiplying this, yeah. Yes?
But here, if we multiply it, we get the area of that under the function gx.
I will get the area. So basically what I am doing is I am integrating f x naught, okay, into g of x, okay, dx. So this is x. So if I do this, I am multiplying these two functions, that is fx naught and g of x, and then integrating from minus infinity to infinity. Okay. So now you look at a situation, my epsilon naught, because then it will be easy for you to answer. So now epsilon naught, not epsilon, okay, this is x0 minus epsilon and x0 plus epsilon. Okay. So now epsilon goes to 0. So that means this width will come to close to x0 and the height will goes to infinity. In infinity. Now what will be the area? What will be the product of this when epsilon tends to 0? It will be the function g of x at that point. Okay, the g of x at that point. So that is the reason this expression is coming. Again, let us go back to the tan hyperbolic x by epsilon, okay, and limit epsilon tends to 0. So this you know that this is equal to, this is epsilon of x or sine function, right?
Yes.
Okay, so now let me take the derivative of this function. What is the derivative of tan hyperbolic? What is the derivative of tan hyperbolic? Okay, so you can find out it is basically sec hyperbolic square. Okay, so here what you get is, so tan hyperbolic x d by dx is equal to sec h square x. Okay, so what will be derivative of tan hyperbolic x by epsilon?
So 1 by epsilon sec h square.
1 by epsilon Okay, so if you do not understand, now there is an exercise. Go and find out the derivative of tan hyperbolic s, which is equal to sec hyperbolic square, square of the sec hyperbolic. Okay, so that you do as an exercise. Okay, and yeah, so now let us take, so if you take the limit epsilon tends to 0 in the right hand side, what are we going to get? Limit epsilon tends to 0. So if you plot sec hyperbolic square, how does it look like? What is the sec hyperbolic square plot? Yeah. So what is sec hyperbolic x? Which is equal to 2 divided by e raised to x plus e power minus x, right? So when x tends to 0, what x is equal to 0, what is the value? 1. When x tends to infinity, what is the value? 0. When x tends to minus infinity, what is the value? 0. You can see that there is no maximum or minimum. What is the slope at x is equal to 0? Okay, so this is basically sec hyperbolic x. So if you take the square, there is a slight change in the function, but it still will looks like the as a function it will look like this. Okay, so when you integrate this function from minus infinity to infinity, what is the integral of minus infinity to infinity sec h square x dx? What will be the integral of that? Because you know that tan hyperbolic x integral is, derivative is sec hyperbolic square. So what will be the integral of this? You can find out the full width at half maximum of this function. So that will be actually proportional to 1 by 2 epsilon, 1 by epsilon. So you find out, okay. So find out the full width at half maximum of this function, then you can see that actually proportional to 1 by epsilon. So when epsilon, yeah,
So, you are finding 1 by the, where is the 1 by 2 from the left?
there is a 1 by 2 here.
Oh, but why are you taking 1 by 2?
No, I want to take that 1 by 2, so you will understand slowly. So the integral of this function is what? From minus infinity to infinity? 1. Okay. So if I don't put 2, the integral will be 2. If I don't put epsilon, integral will be 2 epsilon. So I just want to make it as a normalized function. Basically, normalization means the integral from minus infinity to infinity of this function is 1. So that I want to make sure. So that is the reason I put a 1 by 2. So you will understand why I have done that slowly. Okay, now itself you understand. So now you can see that this width, okay, keep on going to decrease when I increase the epsilon, and the height. So you can see that height of this function, when epsilon tends to 0, it will go to infinity, right? So sec hyperbolic square x by epsilon divided by 1 by 2 epsilon. When epsilon tends to 0, so this function, because this will give you a constant value, but 1 by 2 epsilon is there. So when epsilon tends to 0, this height goes to infinity. Okay. So now you see that two properties of delta function is already met. One is the integral of that function is 1. Second one is when epsilon tends to 0, the width will goes to 0 and height will goes to infinity. So that is the basically two basic properties of a delta function. Height goes to 0 when x is equal to x0 of a delta function, and the everywhere else the function value will be 0. So I can say that when limit epsilon tends to 0, 1 by 2 epsilon sec hyperbolic square x by epsilon equal to delta x. Okay. So this, you have this. Okay. So that is why I was, now you understood why 1 by 2 epsilon, right? Because this 2 is not there, I have to write it as a 2 delta x. So that is the reason. So d by dx of tan hyperbolic x by epsilon is basically equal to 1 by epsilon sec hyperbolic square x by epsilon. Now, when I take limit epsilon tends to 0, what happens to the right hand side? So here also I have to put limit epsilon tends to 0. So what I get in the right hand side? 2 delta x. I get 2 delta x. So what about the left hand side? Limit epsilon tends to 0 d by dx tan hyperbolic x by epsilon. D by dx of epsilon of x. But you have the relation between epsilon of x and theta of x. What was that? One plus theta of x divided by 2. Okay, so the other way around, theta of x is equal to 1 plus epsilon x by 2. So what is d epsilon x by dx from this? What is the derivative of sine function in terms of theta? D epsilon by dx is equal to 2 d theta by dx. So what I am going to get here is, so from this I can see that derivative of theta function is equal to delta function. So these are all very important identities, okay? So when you take the derivative of theta function, so basically that is very clear because you know the theta function. So basically this is up to here 0 and 1, okay? So when you take the derivative of this, obviously, so all other places it will be 0, okay? And here it goes to very high value. So any questions so far?
Sir, I have a doubt.
Yeah.
How is epsilon tends to 0 d by dx of tan hyperbolic equal to d by dx of epsilon?
Can you repeat?
Limit epsilon tends to 0.
Louder, louder.
Limit epsilon tends to 0.
Okay.
D by dx of tan hyperbolic x by e.
Yeah.
So that you said was equal to d by dx of epsilon of x.
D by dx of epsilon of x. Yes.
Yeah, that part I got confused. So,
Yeah. So what is the confusion here?
sorry about it. Got noise.
Clear?
Yeah, clear.
Okay. So is there any other question? Okay, so in the next class what we are going to do is the delta, because now you have the relation between delta with sec hyperbolic, okay, and theta of x. So just one question, whether you understood or not. So e power minus s square ax square, this is a Gaussian function, right? This is a Gaussian function. Can I write down this Gaussian as delta function? Question clear?
Yes.
Okay. So now when you come to the next class, what you do is find out the full width at half maximum of the Gaussian function. Okay. Then you find out how do you write down that as a delta function. Obviously, integral is not 1 here, you know that it is root pi by a, right, when minus infinity to infinity. So you may have to divide with that quantity. Then what is the condition on a? So that will give you that. So there are so many functions, okay, you can write it as a delta function under some limit, okay. So that is the one of the question you can expect, okay. So that for that you should know what you have to do is you have to find out whether the integral is actually 1 and the function is under certain limit goes to 0 everywhere else other than 1 point, okay. So if these two conditions are satisfied, you can actually write down that function as a delta function. Yeah.
I have a doubt that why we are writing a lot of functions as delta function. Like, what is the use?
Yeah, so that's what. So now we are going to, when we a little later on, we will actually write down certain things, okay, when you start doing the physics, okay, because certain point, see, you have some integral, okay, so you have limit, but you know that because of this is a very important okay, so you can actually write down this as f of x naught clearly, right? So you can do this integral very easily. And another thing you are going to learn is basically next class I am going to teach you that what is the Fourier transform? We already learned Fourier transform, right?
No, sir, not now.
Not now. Okay, so Fourier transform of a one constant function is actually delta function. So there are so many instances you can actually write down your function as a delta function. If it is possible to do that, your calculation will become simplified. Okay, you can simplify that easily. So even find out the Fourier transform of I will define that Fourier transform in the next class, but I will not be teaching in general the Fourier transform in our course, but at least for our purpose. So to understand the Fourier transform of a constant function is a delta function. Okay, so that I will do in the next class. So from there you can see that I have to use the property sin x by x, integral sin x by x. So already we have done that integral in the last class. So sin x by x I can actually write it as a integral from minus infinity equal to 1, and I can also write it as a delta function. So using that property I can actually solve the Fourier transform of a constant. So that I will do it in the next class. So similarly, so many places you can use this writing certain functions in terms of delta function so that it will simplify your calculations.
Thank you, sir.
Yeah, okay, I'll stop now.
Sir, you haven't taken our attendance.
Anyway, it is automatically done in the Teams.
Okay, sir.
Yeah.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.